Welcome to webinars from anywhere. We'll begin in just a moment. We still have some attendees filing in. Give us just 1 minute and we'll begin the presentation. Hello and welcome to webinars from anywhere. I'm Silas Robertson. I'll be your host and moderator today. Today we're going to have a really cool topic, which is LMI 3D vision used with your universal robots. We have our panelist, Chris McMonagle from LMI, has fantastic background in vision, worked at an integration company before and solutions provider, and now works with us at LMI on their sensor and vision technologies. He'll be joined by Mike Fisher, who's a senior applications engineer, also just a fantastic multi-decade experience with vision systems. And he'll be doing a live demonstration at the end for us, showing us the use of the LMI with the UR robot. Just a little bit of housekeeping. In your user panel, you'll see a little question mark. That question mark will allow you to ask questions during the presentation. We're going to go ahead and gather those. I'll answer some in the background if I can, but we'll gather them for the whole group and answer them at the end of the presentation. Presentation will last about 30 to 45 minutes. Again, please feel free to interact in the texting format, and we'll get started. Chris, are you live and ready to go?
Yeah, can you hear me?
Yeah, perfect. Please continue and get us started.
Excellent. Thanks, Silas. Yeah, Silas mentioned, my name is Chris McMonagle. I'm a territory manager for LMI Technologies. Today we're going to be looking at 3D vision when working with universal robots. So first thing we'll do is we'll do a quick overview as far as LMI Technologies and what we provide. And we are a 3D sensor manufacturer providing technology that enables you to do a measurement of shape. So if you need to measure a variety of complex components, this is where we can provide lots of high valuable data for these type of measurements. They're typically used for inline 100% scanning and inspection for a variety of different types of applications. So whether it's food, inline electronics, there's many applications in which our 3D technology provides valuable feedback to the manufacturing process. Not only is it utilized for inline inspection, but these can also be mounted to robots or guide robots to perform certain functionality, especially when it comes to optimization. So after we measure something, can we tell a downstream device to perform a specific operation based off of the results? Now, our flagship solution is our GoCater all-in-one sensor, and this includes both laser and structured light sensors, so laser line scanners along with snapshot sensors. What's really nice about the GoCater is it's all encompassing all-in-one design. You scan, measure, and control all in a single device. So they're factory calibrated. Right out of the box, you're going to get very accurate measurements. And because we produce our own laser and structured light source, we do not need to provide external lighting. Very ruggedized, so built for the factory, IP67 rating. We have a variety of different sensor types that range in fields of view from 10 millimeters all the way up to 2 meters in field of view. And embedded in the sensor is a web-based user interface with lots of built-in measurement tools. So you simply need to plug in the sensor into a PC, and you can visualize and access that sensor's web interface just by entering the IP address. And inside that IP address or in that web interface, you do scanning. There's a lot of built-in measurement tools when it comes to surface data. And then something on the right, you'll see that we can take not only surface data, but profile measurements of a cross-section, let's say. Some other built-in measurement tools as we continue to improve the GoCater interface include stuff like surface segmentation, barcode reading, or something on the right would be for a glue bead inspection, so measuring many cross-sections across a specific profile. GoCaters also have a flexible I/O control, so you can communicate with external systems, PLCs, or even robots. So making that very easy to communicate with external devices. So our main focus today is the integration or vision, 3D vision with universal robots. So LMI and the GoCater do have a UR cap. And back in 2018, we started with support of our Snapshot G3 sensors. And there were 3 sensor options and with some smaller fields of view up to 150 millimeters. As of this month, we now support our full line of G2 sensors, which is our laser line sensors. And this really opens up a lot more applications when utilizing 3D sensor technology from LMI, because we have 25 sensor options in this G2 family and fields of view up to 2 meters. So the scale and size of objects in which you can scan has greatly increased. So as we mentioned, the vast number of new options we have in the G2 line opens up many doors, while we still maintain our snapshot sensors as a very great option for your application. Now, the difference between a laser line and a structured light sensor is laser line, you're gonna be moving while you're scanning, or you can go to a discrete location and measure a profile. Snapshot sensors are purely image stationary data acquisition. Now in the UR cap, it's all built into the user interface or the teach pendant for the universal robot when it comes to calibrating the coordinate system of the sensor to the robot. And same thing when it comes to triggering scanning. So it's very easy to deploy, making and allowing the end user to get to the solution much quicker. Our UR cap is available for download at our website. So if you already have a GoCater, you can simply load the UR cap into your universal robot, and it's free and readily available. Now we look at some typical applications for this. This could be robot pick and place, so guiding a robot where to go grab an object. Seam tracking, so if you're doing welding or maybe weld inspection, this will allow you to monitor a specific seam in this case. We do adhesive bead inspection, so while you're laying down glue bead, you can measure the fill volume or adjust in real time. We see a lot of applications in automotive and aerospace, so when it comes to flush and gap, countersunk holes, position of specific objects within an assembly, we can quickly go to these locations and verify that they conform and meet the engineering drawing. And then on the left, we can also see some battery inspection. Here is a system that is doing flush and gap inspection. So in this case, you have 4 universal robots moving to locations within a car body panel and verifying that the form fit and flush and gap is good on this particular car. Now with some of our laser line scanners, we can really open up some larger object scanning. So in this case, we'll see a 2490, which is our largest field of view sensor, scanning pallets. So very large objects with very good resolution and data quality. And with this, we can isolate specific individual components and identify their X, Y, and Z location to guide the robot to, let's say, go and pick up these objects. So again, this 2490 is a very large field of view. You can use it for packaging, palletizing, loading and unloading of particular objects. And just for scale of reference, here would be a scan of a very large car in this case. So now we'll jump over to Mike Fisher, who will do a live demonstration and give you guys an overview of our URCAP.
All right, Mike, I think you have presentation rights now.
Great. Can you see my screen with the outline page?
Yes.
Okay, cool. And you can see my webcam? Just want to make sure we got.
Definitely.
So you're seeing what I think you're seeing. Great. Well, welcome everybody to this webinar on LMI 3D vision with UR integration. We're going to focus on the new line profiler support, but as Chris mentioned, we've been UR Plus certified for about 2 years. We've supported the snapshot line of sensors. We've had a UR cap out for about 2 years. We've just recently added support for the line profilers, which allows us to scan much larger parts. So one of the slides Chris showed featured the 2490, which has a field of view up to 6 feet across, so we can scan much bigger targets. Let me describe my setup. First, you can see my webcam. I have a UR5E right here, and it has a Gocator 2350 mounted to it. This is kind of our mid-range Gocator line profiler. We have smaller units that give you a couple microns of accuracy, and then, as we talked about, we have larger units that give you a 6 foot wide field of view, so you can kind of select based on your speed, your accuracy requirements, which sensor works for you. What I'm going to show you today, the demo using the 2350, we could do with a smaller unit or a larger unit. The software is exactly the same. I have a custom bracket that attaches this to the UR robot. We do sell, I believe, 1 or 2 brackets. Customers generally make their own. You can 3D print them or machine them to accommodate whatever gripper you want to use. I do not have a gripper mounted. So I have a gripper, but it's not mounted. Instead, I have kind of a simulated gripper with this ruler, and I've configured my TCP, my tool center point, to be the end of that ruler. So hopefully when we do like a guidance application, a pick and place application, that is the point that will drive simulating how you would move a gripper into place. As far as samples, we're going to be using 2 balls and a block. We're going to be using these 2 balls for our calibration, and then I'm going to be scanning a block, which is just a random target, but it allows us to showcase some of the nice 3D tools and benefits of using 3D vision over conventional 2D vision. All right, as far as software goes, I have a browser which is connected to my Gocator, and I'm going to be doing my calibration through this interface, and then I'm going to have a job loaded to do, hopefully, some pick and place operations. And then I also have a VNC viewer, which allows me to view my UR teach pendant through my computer. So it's much easier for you guys to all see what I'm seeing on the teach pendant through this window, and I can control my robot. I can configure my program through this VNC viewer, so that's a nice little utility. Let me go ahead and load a new program, and we can go ahead and get started. Enough about the setup. Let's go ahead and show some integration. I want to build a program and do pretty much everything from scratch to show how easy it is. So let's go ahead and load a new program. Discard my changes. I do have my TCP configured. You can see what it is here, which is about where I described at the tip of that ruler. So it's about 170 millimeters from the tool flange over a little bit on one side of the Gocator. And let's go ahead and do some hand-eye calibration. Well, actually, I can show kind of what the UR cap gives us. So I do have the LMI UR cap loaded. The way to do that is to go into the settings, UR caps, and if I didn't have the Gocator UR cap already in there, I can just add it, but I do have it already loaded, and what that gives me is a couple of things. It gives me a installation tab here for doing hand-eye calibration. I'll walk through this in a minute. And it also gives me, in my program section, a bunch of new functions. We'll cover most of these: Gocator receive, scan, trigger, calibrate, connect, and load job. So it allows me to control, through the UR robot, it allows me to control my 3D system and receive information back from it. So right now, the robot has its coordinate space, and the laser line profiler has its own coordinate space. Our 3D systems come factory calibrated, so you don't need to use a checkerboard or any kind of fancy equipment to calibrate them. Every unit is recorded in millimeters by default. But right now, the line profiler doesn't know where the robot is, and the robot doesn't know where the 3D system is. So there's a hand-eye calibration process that you have to go through so that you can transform from one coordinate space to the other. And hopefully we'll show you that that's fairly easy to do. So first, I need to load the right job into my Gocator. Right now, my Gocator has blank job. I've got one job stored. If I look at my job list, there's a new job, and then something that I might load later when we do some pick and place. But I need to load a special job to do the hand-eye calibration, and I can do that through the robot. So I'm connected to my sensor. When I hit the setup job button, the UR robot is actually going to download a special job to my Gocator. I might have to disconnect and reconnect. Okay, it says setup job completed successfully. And now when I switch over to my Gocator, refresh this window, I should see a new job loaded. I've got this job called Go Robot Calib. And that job consists of one tool, which is this surface ball bar tool. And what this tool does is it looks for a ball bar, and it's going to find two spheres and measure the distance between them and find the plane that they sit on, and then send those values to my robot. So I've done everything I need to on the 3D system, and now on the robot end, I need to add a Gocator calibrate tool. So again, I already added a new program. I'm going to run this once so the program doesn't loop forever, and I'll add Gocator calibrate. The sensor IP address is automatically found. The job name is going to be Go Robot Calib. And these default settings will work fine. I'll talk about these in a minute. But let's go ahead and just run this, and hopefully we'll see our robot move. We'll see the 3D system laser line turn on, and we'll scan the ball bar. Now I'm going to set this up first with just one ball to show an error. Let me run this. Give it a second, and hopefully, if you guys can see my video, you'll see the laser line from the robot, from the 3D system turn on. My ball is going to get scanned, and let's see what happened there. So we scanned it once. Just trying to communicate to my Gocator. I may need to stop it and restart it. So let's go ahead and start that again. Bear with me for a minute here.
While we're waiting for Mike to reconnect, it looks like maybe an Ethernet connection. Work on that. I'm going to bring up a couple questions, while you work through that, Mike, that maybe Chris can help us out with. One was, Chris, if you could compare, why you would use 3D vision versus 2D vision in an application. Could you go over that for the audience?
Yeah, so 3D, we're going to be able to see a lot of, let's say, height measurements. So not only are you going to get a 2D measurement, but you can also measure the distance between something. So that's very valuable if you're measuring step heights or you need to guide the robot to a specific location. It's not just based off of an XY plane, but you can also find it something that's closer to you. Also 3D, because we produce our own laser source or light source, we're generally not affected by ambient lighting conditions or changing in lighting conditions. So, you can ensure that you're not going to see changes in the environment affecting the results or where your robot's going after that.
Okay, great. Another quick question that came up was, as far as like other products, you'd shown sort of welding applications, adhesive applications. There are some other UR Plus products like Vectus and Arsenal. Vectus does welding and Arsenal does adhesives. Are you able to work alongside of those? So you can buy the UR Plus from LMI and the UR Plus from Arsenal, for example. Would that work out fine?
Yes, exactly. So this is a key differentiator in why UR has built this ecosystem. They make it very easy for multiple UR Plus components to work easily together. And as Mike is showing, he's working in the UR robot program here. You could have a gripper there. You could have another UR Plus product that programs seamlessly alongside the Go-Cater. So as Mike's showing today, he's going to show a pointer, but it could be a gripper that goes and picks up an object here, and that's what makes that easy.
Okay, got it. So not only can you do these other products, like solutions, like a welding, but you can even have like a Robotique gripper that has UR Plus, and so you can have multiples of those running all at the same time.
Exactly. Yep.
Okay. Sounds good. And then, as far as getting it set up, is there a different UR Plus per LMI product, or is it just one UR Plus that applies to all of them?
I think Mike, can you confirm that? I believe it's the same UR cap.
It's one UR cap, yeah, and it works with the snapshots and the line profile.
Okay, great. Sorry, I just had some more questions coming in, and so I was trying to read those at the same time. Sorry for the distraction. Are you ready to go, Mike?
Yeah, let's try this again. So I restarted the sensor, reconnected to it, and here we'll see our surface ball bar tool. If I view my image in 3D mode, the surface ball bar looks for two spheres and a plane. And I was going to show the error, but now I'm just going to try to find both balls and show the tool working. Let me switch over to my robot. I've got the calibrate function in there, and hopefully if I run it, the robot should scan multiple times over the ball bar at different positions.
Okay, sounds good. I'm going to go ahead and let you start that, Mike. I'm Blaine. I know you just typed in a question. I'm going to get that here after Mike finishes the presentation of kind of the demo. Hang on real tight. Go ahead, Mike, whenever you're ready.
All right, great. Let me get my ball bars a little bit here. So I do want to confirm that I have my TCP set, and it looks like I do. And then I should be able to run my program here. We'll scan a few times. And you'll see the live image here. Hopefully we'll find both balls. All right, so that was the hand-eye calibration. For my ball bar, I really just used 2 spheres on a flat plane. We do sell, a NIST traceable, highly accurate ball bar for a demo like I'm doing today. What I'm using works fine, but if you need to pick apart and put it in a very specific location, you would want to use a proper ball bar. But again, for what I'm doing today, this works fine. As long as I have 2 balls in the field of view and I scan them correctly, this works. And now on my robot side, everything's calibrated. And I've generated a transformation matrix. So now the robot knows where the 3D system is. And if I find points with my 3D system, I can relay them back to the robot and they're sent back in meaningful coordinates. So that's the calibration. Now I can hide the calibration and create a program. And I want to do this from scratch. What I'm going to do is scan my block instead of these round spheres. And I can also load a different program in my GoCater. So I have the program called UR block, which is going to look for exactly that, a block on a flat plane. So load that job, and then on the robot side, I'm going to build a very simple program that is going to loop forever. I'm going to start with a connection to my GoCater at the correct IP address, and here's where I'm going to load my calibration matrix. Cool. And here's my robot program. I might have to calibrate again. I don't know if this calibration matrix looks good, but we'll find out. So my robot program is going to start with a move to home. We'll call this position home. So we'll move home, and then we'll do a GoCater scan. So this is one of the tools available from the URCAP GoCater scan. And let's just go ahead and do this. We'll move home, scan, and then wait for 2 seconds. Set our waypoint. There we go. And let's go ahead and run this. So we should see the robot move. We've set our scan up for it to move at a speed of 100 millimeters per second or 150 millimeters. Looks like our home position is off. So it does look like home is off. I am going to go through this calibrate one more time.
And Mike, related to the calibration, we had a question about from Blaine. What is the precision of the scan data post hand-eye calibration with the UR? Can you give us some indication of that while you're working through this?
Yeah, that's a good question. It really depends on what sensor you're using. If you calibrate it correctly, then I think you would go by the resolution and the repeatability spec of the locator. So our 2510 is maybe 7 microns repeatability. The 2490 is closer to 1 millimeter repeatability in the X and Y.
Sounds great. And while you're working through this, Mike, Chris, this is probably a question for you. I answered it a little bit my way, but I'd love to get your input on this. This is from Eduardo. He was asking, could the robot be fitted with a gripper to be able to pick tomatoes, and not necessarily tomatoes specifically, but have you used and seen the Go-Cater be used with produce and then a soft gripper technology to pick and place?
Yeah, certainly. So, imagine, I've seen many applications where fruit or plants or something is coming down a conveyor, and it can be scanned by the laser line profiler to tell the robot where it is to go pick it up with, a soft gripper. And so, these are applications where the Go-Cater can either be mounted to the robot or it could be mounted above the conveyor, telling the robot where that produce is coming down the line. And especially when you get, let's say many in a line, or maybe they're stacked at different heights and levels, it'll, not only give it its X and Y position, but, where's maybe the center of gravity of that object to go grab it.
Got it. Eduardo's follow-up question, how about off the plant? Have you ever picked off the plant?
I have not seen that. Maybe Dan or somebody else has, but I don't see why it wouldn't be feasible.
I have not seen it either, but it's certainly, it's just a different, I guess it's just a little more complicated motion than picking off conveyor from the robot's standpoint, but from a measurement standpoint, shouldn't be a big deal on our side.
Yeah, I think we've toyed around with it and played with it. We've never actually, Eduardo, had a specific application for that, but technically it should be very feasible.
You could almost imagine these spheres that Mike is scanning as maybe fruit or nuts or something on a plant. You just need to guide the sensor to scan in a specific region, and we can go and locate those objects. How far are they away from the sensor? How far away from the robot? And guide it from there.
Related to that question, this is my own addition to Eduardo's question. From a sizing standpoint, can you also do some classification using the Go-Cater with the UR? Is there some intelligence in that sensor that would help us there?
Can you clarify the question?
I guess maybe how about small, medium, and large? Let's say we had small, medium, and large tomatoes. Could we get some volumetric information and sort those?
Yeah, certainly. So, as we scan them, we'll be able to kind of segment what we find. And then Go-Cater does have built-in measurement tools to measure maybe like a bounding box. You can measure the length and width of it, but also we have volumetric measurement tools so you can measure how big is that fruit or how big is that object, and do I need to sort it into a specific bin based off of its size. So these are decisions that could be made within the Go-Cater to send external protocol based off of decisions that are made and values that are obtained. So you'll see even here, Mike has a bounding box and he's identifying where that block is, where's the normal vector of that block. So yeah, we can also measure the volume of that block in this case.
Sounds good. One of the interesting things that Mike was talking about, or maybe it was you, was that since it does supply its own light source, that it's more immune to lighting effects, which does plague a lot of 2D vision. It does have some limitations, though. I assume, Chris, meaning mirror-like reflections or those sorts of things. Could you comment on that?
Yeah, so highly reflective surfaces tend to shine back into the sensor and can cause some reflection or noise. We do have some filtering tools to account for that, and exposure settings to account for that. So we try to optimize the sensor as much as possible for the application in mind. And then we do have some sensors that operate outdoors. So depending upon the application, we'd want to review that and identify which sensor is going to work best, and then help guide which settings are going to be optimal for the application.
That's good. Could you comment a little bit on IP rating of the sensor? I can comment on the UR a little bit as well, but any particular IP rating of the sensor?
Yeah, so all of our sensors are IP67 rated, so they're dust-proof, waterproof, very ruggedized. So we could run these in very harsh environments without it damaging the sensor itself. So only thing that we find sometimes is you may have to periodically clean the sensor or maybe the lenses to ensure maybe if there's any debris or dust in the air. But overall, very ruggedized and built for factory environments.
Sounds good, Chris. And just to follow up on that, the robot is not IP67 rated. So, for those more, wash down, spray, even external environments, sort of outside environments, you would want to look at a suit or some sort of protection covering for the robot. The sensor would sounds like it would be okay in most of those situations.
Correct. And it looks like, Mike, looks like you're ready.
Yeah. I don't know if this calibration matrix, I was expecting something different, but we can try it. Definitely the scan is working right now. So if I put this into, if I run the program, I'm gonna, it's gonna first connect to my 3D system, and then it's gonna go home, execute a scan, and wait 2 seconds. So we'll see this image here update once in a while as my block gets scanned. And one thing I forgot to mention, that the scan settings are configured through the UR robot. So I have this locator scan function, which specifies the surface length, speed, acceleration, and that gets sent to my 3D system. So under scan settings, you have trigger, time trigger, and then surface generation software, and length is 150. So if I stop this and change, instead of 150, if I want to acquire a longer region, say 200 millimeters, now when I run this, it should overwrite the settings in the 3D system through the robot. I might have to refresh the screen here. Now surface generation should, once it starts writing, change that, and you can see my surface length is longer. We need to refresh again. There's 200 millimeters. So you do control all that through the robot. And the image that I'm showing is a 3D scan for my 3D system. And again, that gets updated every time a new scan is performed. So now let's do some communication, some additional functions through the UR-CAT. There's a locator receive, and I can specify what I want to get from my 3D system. So just let's go ahead and get a time value, which is that measurement ID. It's a single measurement. Let's go ahead and run that. Measurement ID corresponds to a time value here in my program, which is actually the cycle time of my first tool. So there's a surface filter that runs 21.927 milliseconds, and that value changes 22.864, and I should get that value here in my robot. So it's just showing passing values from the 3D system into the robot. I don't really care about cycle time value. What I want is the location of that block. So I'm going to change this receive to pull in a XYZ RPY. So not just the position, XYZ position, but also the roll pitch yaw, which is good 3D information that would let me guide my system to come in at the right angle and pick that part up. And now instead of calling this time, I'll call it block. And the ID is going to be, I believe it's 7 for my program. So the value that I'm sending is the result of this feature robot pose tool, which uses a couple different tools, surface plane, surface bounding box, to get all the information you need in order to pick this part up, the XYZ and the roll, the yaw as well. And through the transformation matrix that I built with my hand-eye calibration, I convert these from Gocator space to robot space. So now when I run this, the values that I see in my 3D system are going to be different than what I see in the UR robot. So under variables, give us a chance to scan, and we should see a new variable called block. And these are the new XYZ RPY values in the robot space. So we're getting short on time. I am going to try to do a move here. I don't know if my transformation matrix was set up correctly, but the way that you would use this value is once you receive the position of that block, you would then set up a move to not a fixed waypoint, but the variable position that block. Let me actually stop this and slow down the move just so we don't go too fast. Again, we'll see it scan, and hopefully if everything's set up right, the tip of that end effector. Oh, I actually forgot to do a flip. Stop this under my Gocator receive, flip around X. I did do that. So I think my transformation matrix is wrong, but that's the way you would do it if you had this set up right. I think this value is supposed to be a little different, so I'd have to recalibrate with my ball bar or my balls. But this is essentially the program you would use for a pick and place application. And I think we're short on time, so I'm not going to try to debug this.
No problem, Mike. That's live presentations and live TV. I think we got a good view of the 3D scanning, so appreciate that. I'm going to turn it over to Chris to kind of wrap it up for us and bring it home for everybody. Go ahead, Chris. You're on mute real quick, Chris.
Yeah, thank you. Is there any other questions I think that you had, Silas?
No, we were answering them during the presentation, so I think
Okay.
good.
Yeah, so definitely something that we wanted to mention is if you want to reach out to Olympus Controls or LMI, we can do sample testing. We can send parts to Mike and give you a demonstration on your particular part. So this could be more of a one-on-one session to make sure that we show you how this functionality works. So feel free to reach out to us and we'd be happy to test for you.
All right, that's great. Thanks again, everybody, for joining Webinars from Anywhere. Please join us again for a future show. Thanks again.